All right, everybody, here it is. Time for the big, scary triple lab. You've done all the data. Now we've just got to do some entering. If I have a cursor here. There we go. Oh, my goodness, that's a lot. So let's do the front cover together. Not too bad. What we've been doing, absorption and radiation. Now, I'm not going to do sciencey, scary definitions here. Let's just keep it simple. Absorption would be like when an object, I don't know, how do you want to say it? Gathers energy. I don't know if that's the perfect word, but I also like these definitions to be like usable too. When an object's radiation then would be when it gives it back off to the room. Maybe gains and loses would have been a good way to say it. When it loses its energy. Now I found my infrared camera, though I haven't found a charger. I got to get it charged up, and I'm gonna have people like you can play with this for a few minutes during class. Walk around, check some things out, because what we want to see is that when objects are losing their heat energy, they give off infrared radiation. I guess I got to make the whole text box big, but let's make the spelling of that infrared, INFRARED, which is like if I told you at the beginning, hey, you're going to take a lamp, put it onto a black can for 15 minutes, you're going to say like, well, it's going to heat up, and then I said, yep, and then you're going to take it away for 15 minutes. You're going to say, well, it's going to cool down. Like that's all easy stuff, right? So yeah, it is, but there's also a trick. The visible light that heats Earth's surface, and you should have done this in the notes in lesson B, has a shorter wavelength. Energy transferred back to the atmosphere, this infrared, has a longer wavelength. Then this longer wavelength, again, we'll write infrared, INFRARED. This longer wavelength energy does not escape the atmosphere. Rather, it gets trapped and it warms the atmosphere up. This is known as the greenhouse effect. And as we talked about in class on Monday, if you've been in a greenhouse or a hoop house or even a parked car in a parking lot when the sun's up, you've experienced this. The sun can go right through the windows, no problem. If it hits something shiny, it goes right back out through the windows. But what about the sun's energy that gets absorbed by things like the seats or the dashboard or whatever? Those then heat up. They're warmer, so they're giving off more infrared energy. And infrared energy can't escape the glass. So the net result is that it gets warmer in there. It's why greenhouses work. And like that's why you want to put thermal masses in greenhouses. Plastic jugs of water painted black are excellent. Why? Using some of the things that maybe you notice in this lab. What is it about black? What is it about water? I guess I should answer those questions because we're on video. Like you saw in Black versus Shiny, black is better at absorbing that energy. Why water? Water's hard to heat up, but it's also it cools down very slowly, so it's a good like holder of energy. We have to figure out why. So yeah, so that's like how greenhouses work, right? Our atmosphere does the same thing, and it's great. We love it because otherwise, if we turned away from the sun when it was what we call nighttime, if we didn't have a greenhouse effect, we would like, and all the energy just left back out into space, it would plummet temperature wise. So as evidence for that, if you go to the moon, temperatures vary. I don't remember the exact numbers, but it's somewhere around 250 degrees at night. Well, they're about the same, honestly. It's about negative 250 at night and about positive 250 during the day. Let's double check that. So the internet tells me 260 and 280. So it's like that much of a swing. We'll call it about 250. About a 500-degree swing from day to night. Now, life would not have evolved in conditions like that on Earth. We like the stability of when the Earth spins away and it's dark, the atmosphere, the greenhouse effect holds on to some of our heat energy. However, too much of a good thing can be bad. There's a runaway greenhouse effect on Venus, the planet Venus. That's the hottest planet. It's not the closest to the sun. Mercury first, then Venus. Um, but an outrageous amount of greenhouse gases in their atmosphere. The temperature is almost 900 degrees on the surface, hot enough to melt lead. And they've tried to look it up if you want to. They've tried sending a couple of probes there to like check out surfaces, and it's very difficult to keep computers operating in those extreme conditions. So too many greenhouse gases, like CO2 or methane, water vapor counts on the list too. But those are the big two that like we contribute to as humans. Too many of those heat planets. So we like our atmosphere to be an efficient absorber of energy. It keeps the night side of the planet warm. But we humans, by adding too many of these gases, are making it too efficient, which means that the atmosphere is going to be warmer. And the implications for that then we'll have to look at as we go through the course, but they can be significant. To the societies that we've set up on this planet that we're trying to keep stable, we're doing that in a continually dynamic and unstable atmosphere. So, what we should see with our data, how this should have worked. Did your experiments work? We'll find out. Sometimes because we've got equipment that's only so, and the labs are a little chaotic in here with especially the bigger classes. Maybe they didn't work perfectly for you. What we should see with our data, and what's a bigger science rule, a good absorber is also a good radiator. So, sand versus water. As I walked around, most people were getting good data. The sand heated up more. It also cooled off more. Now, you know this if you've been to the beach. If you've walked around on the sand in bare feet and had like pain in your feet because the sand is very hot, what do? You run to the water to cool them off. Think about it in your head. If the sand and the water heated equally, that water would be equally as hot as the sand. You'd be like running into very, very, very hot water. That would be really bizarre. So that experiment, even if your little lab setup didn't work, that experiment of running around on the beach in bare feet is a good demonstration of this. The sand is a good absorber of energy. It heats up very quickly. The water doesn't heat up very quickly. But when it cools, the sand cools down more and the water actually holds onto its energy a little bit better. So that's going to have huge implications from day to night. If you live near the lake, that lake can actually stay a little bit warmer if the night gets cold, and from season to season. As we go from summer, when the lake comes up in temperature very slowly, and then we go into winter, the land gets very cold, but the temperature of the water near the lake, the temperature of the water is warmer, and it keeps that area a little bit warmer. It does a good job of like holding on to that heat energy. And that's going to be like something we're going to work on. We got a lot to go with that. This is just, hey, sand heats up more and cools down more. Black can versus shiny can. How'd that work? Greenhouse effect one. How'd that work? All right. So your job, it's going to be a little bit litigious, a little bit of work, but you've done all the work already. This should just be like transcribing sand numbers, water numbers, and then we'll graph. There are 30 boxes here for the 30 minutes. So 0, 1, 2, 3, 4. Your y-axis, we might have to work together a little bit to figure out what's a good y-axis. I wouldn't do it like you have to fit all your data on there, and we want the graph to fill some space. So don't start going 0, 1, 2, 3, 4 if you got to make it to 200. If you're struggling with that, let me know. Let's work it out. These numbers you should have done in class. How much did the sand go up, water go up, sand go down, water go down? But you could also still figure them out now. Same thing for black for shiny. Same thing for the covered versus uncovered one. Rate of change problems. You should have done that already up there in the survival guide. And let's talk specific heat real quick, and then the bell's going to ring, and we're off and running. Specific heat is specifically how much energy does it take to heat something up? How many joules, which is a unit of energy, does it take to heat a gram of something by a degree Celsius? So look at this list. What's very high on this list that you notice? Liquid water. So what we're saying is that liquid water takes the most energy to heat this many grams of it by this many degrees C. It's a high number. So if I added an equal amount of energy to all of these different things, water is going to be the one that changes temperature the least. Generally, as people are learning earth science, they find that a little bit like weird and surprising because you boil water all the time. I want to make macaroni and cheese, you boil water. I'm very used to it. I know it's not that hard like my stove does it, right? And you probably don't have much experience grabbing a piece of granite and wanting to heat it with a lower specific heat, like it's just unusual, right? But even though it's common, it's a specific and like vital thing for many lessons we got to do. There's the bell. I know you hate that. Vital thing we got to do for how water behaves, and that is that it's very difficult to heat up. It takes a lot of energy to get a certain mass of it to go up by a certain number of degrees C. And it also, therefore, cools down very slowly. That should help you with those two. Good old reasons, questions. Conclusions going to be a whole nother lesson we do in class. This should take you a few minutes, though. Good luck with all of it. Hope you do well. So long.